Hello students, welcome back. Let's go to section 3, interval estimation for population means. Wait a minute, haven't we done this before? Back in section 1, we had this example problem. Remember? We went through some confidence intervals and confidence bounds for the mean one-way commute distance for all students. Yes, this is for the interval estimation for population mean. We did it, it worked. Why are we doing this again? Well, it worked, but under some special circumstance. Number 1, for large sample size. We have a sample size of 126, that's greater than 100. For population means, the sample size of 100 or more is typically considered as large sample size, so that we can use the normal approximation. Number 2, we have the population standard deviation of 6.2 miles. Remember, I just used a Greek letter here. Greek letters are population parameters and Roman letters are sample statistics. So this is a population standard deviation. And this is highly problematic. We don't even know the population means, so that we are doing all this interval estimation to begin with. But we know the population standard deviation? That doesn't make much sense, does it? In fact, this never happens. In real-life situation, nobody knows anything about any of the population parameter. Of course, everybody knows that they exist, but that's about it. What are their values? Nobody knows. So what do? We have to do some estimation. Point estimation, in this particular case, like this. Remember, SE is sigma over square root of n, and that is for the central limit theorem and also for the sampling distribution of sample means. But we don't know the sigma value. So what do? Let's approximate it with S over square root of n. S is the sample statistic. And now, can we still use the z-curve with this? Good question. Sometimes we can, sometimes we can't. For large sample size, yes, we can for central limit theorem, but for smaller sample size, no, we can't. Now, what if the sample size is small and also we don't know the population standard deviation? We need a new tool, and that new tool here we are going to discuss is students t-distribution. By the way, why is this called students distribution? Well, there's a bit of history behind it. The person who invented it, his real name was Gossett, but due to some copyright issue, he published his results in a pseudonym of student, and that's why the name stuck. I don't like the name, so I'll use the term t-curve, t-distribution, t-score, t-table, etc. In contrast, everything related is normal. I'm going to use the term z-curve, z-table, z-score, things like those. T-curves come with the degree of freedom. And the degree of freedom is actually n-1 in this case. As a matter of fact, this has something to do with the dimension, and this is elementary statistics. So everything we do is going to be one-dimensional. So the degree of freedom we're going to learn is going to be n-1 all the time. In upper level, with some multivariable, then in that case, we may have some two-dimensional quantity with some degree of freedom of n-2, those kind of things, but not at this level. So degree of freedom, for your case, it's n-1 all the time. By the way, here is an interactive visualization of the t-curve, the student's t-curve. And the solid curve is the t-curve, and the dotted red curve is a z-curve, the normal curve. As you can see, the normal curve is more concentrated toward the center, and the t-curve is more spread out. And this particular case here is the degree of freedom of 1, so the sample size must be 2. You see, remember the degree of freedom is n minus 1. So sample size of 2, and then let's increase. As the sample size increases, or equivalently, the degree of freedom increases. And the solid curve, the t curve is approaching the z curve. See, from here, increasing, going up, up, up. We got up to degree of freedom of 10, so the sample size of 11. As for any kind of computation associated to these curves, actually they're the same. Z is n minus center over SC. Likewise, t-score is n minus center over SC. It's the same deal. So n minus center over SC is common, and all the more reason to call this the formula number 1. It's really versatile. Now, before going over to the real application problem, let's have a bit of a decision-making exercise. Please stop the playback and read through. So the first problem is the very same as the one we studied in section 1, except that I explicitly emphasize that this is the population standard deviation, and also I color-coded accordingly. And then the second, change the sample standard deviation. The third and fourth, I adjusted the sample size, but if sample size is small and the probability distribution is really wacky, then we cannot really do too much. So we have additional assumption that the original distribution is normal. Now please note that in these 3 cases, you can use the normal distribution, the z-curve and the z-table. Here, the sample size is large, and also we have the sigma. Here, sample size is large. Even though we don't have sigma, we have only sample standard deviation. Because this is large, yes, we can use normal approximation. This time, the sample size is small, so the central limit theorem will not apply very well, but we do have sigma value, and the original distribution is normal, so we can apply the normal distribution as we did in lesson 7. Remember, in lesson 7, we had a normal distribution, and we tracked down the individual, not a sample, just individual, so the sample of 1. So even for n equals to 1, it worked. So n as 26, yeah, it'll work. The last one here, this one is going to be a t-curve problem. We have smaller sample size, just 26, and we don't know sigma, we only have s, the sample standard deviation. And an additional condition, the original distribution is normal. Let's go back here. I didn't really emphasize the original population distribution is normal. I mean, I did talk about the small sample size and then unknown population standard deviation. That's when we use t-curve, but I didn't really emphasize about this. The original distribution should be normal. That's because the last criterion is pretty much useless for this course. Because whenever you encounter an exam problem or something, any problem, the problem should be solvable. So if the original is not normally distributed and you don't have any of those, then you cannot do that problem. It just doesn't work, so you don't really have to worry about it. So basically it's this. A small or large sample size is usually the rule of thumb, and that usually trumps everything. But in some exceptional cases, you may have to come back and discuss whether the given standard deviation is the population standard deviation or the sample standard deviation. A bit rare, but you may have to consider that. And finally, about this original distribution is normal. At this level, you don't have to worry about it. So, small sample, number 1 criterion. Unknown population standard deviation, very distant number 2. And then still more distant number 3 criterion. I happen to have a bit of time for a bit of some digression. So let me talk about this one a little bit. What if the original population distribution is very, very far from normal? Well, here's an example. Go back to this proportion example. Just one draw of ball or one roll of die, those kind of things, is called Bernoulli random variable, and that's discrete, has only two outcomes, success and failure, and this does not resemble normal at all. So in this case, the t-distribution of these kind of things, none of that will work. So how do we make it work here for section 2? We took large sample size. Not just about 100 or so, but in section 2, we usually have a sample size of 1,000 or more. And that's why it's not anyway close to normal at all. That's why we need bigger sample size. Typically for proportions, we want 1,000 or more. For proportions, typically we want 1,000 or more. Typically for means, 100 or more. So n is 100 or more typically, then you can use normal. Z-curve and Z-table. Now if n is less than 50, then use a t-curve and t-score and t-table. That's usually the case. Now what if we have between 50 and 100? That's a gray area. Wind can blow in any direction. So I'll try to avoid this kind of problem. For example, sample size of 76 or 85 or things like that. I'll try to avoid those. Whenever you encounter those kind of things, it's most likely I'm going to accept both answers as correct answers. But if you see something like n value as 23, most definitely it's going to be a t problem. Oh, excuse me, I take it back. Almost all the time it's going to be a t problem, but in highly exceptional case, you may end up with known population standard deviation versus unknown population deviation. This second criterion as well. So be careful about that. So those kind of decision making, we went through those. All right, so much for digression. And one more digression. Here's a checklist. What to use when. Okay. Now here are some visualizations for confidence intervals and for confidence bounds. But in any case, do you see the gray curve and then the solid colored curve? The gray curve in the background is the normal curve, the Z curve. And then the solid curve is a T curve. And then this T curve has sample size of 5, so the degree of freedom is 4. And if I change that into, say, 10, then as you can see here, the solid curve got closer to the gray curve. And then if you go over to, say, about 50, then you won't see any difference at all. Let's go back down to about default. You'll see that the normal curve is more concentrated towards center. And do you see this dotted line there? That's the endpoint for the confidence interval for the normal curve. So the normal curve has smaller confidence intervals, so smaller margin of error compared with the T curves. So if you can use the normal curve, the Z curve, then you get better result. Okay, so much for visualization.